In this video, we're going to cover the fundamentals of transformations. Now, transformations is one of those topics that tends to trip up a lot of students. And that's often because they're only taught the shortcuts and not the underlying process. That's why in this video, we're going to cover the only process you'll need to apply any transformation. Let's get into it. Before we can get into the specific kinds of transformations, we first need to cover the fundamentals of functions. At a base level, functions turn x values into y values. One way to express this mathematically is with an ordered pair. You have some unique value x, which corresponds to some unique value y. This is where transformations come in. Transformations seek to change this relationship. We start with our original ordered pair xy, and then we map that onto some new ordered pair x prime y prime. Now that you understand this, let's have a look at the three fundamental transformations. There are only three main kinds of transformations. First we have dilations, then we have reflections, and lastly we have translations. You can think of dilations as transformations that stretch a function. You can stretch a function in two axes. You can stretch in the y-axis, vertically, or you can stretch horizontally in the x-axis. There are two main terminologies that your exam might use to express this. Firstly, you could have a dilation along the axis. This means that you have your axis and the dilation moves in the direction along that axis. For example, if your dilation was along the y-axis, then the dilation applies to the y values because it applies along the y-axis. However, dilations can also be applied from the axis. Using the same example, if your dilation is applied from the y-axis, that means it's going away from the y-axis, which is in fact a dilation along the x-axis. Okay, so that's what dilations are, but how do we express them? Dilations are expressed as a coefficient on either the x or y term, depending on what the transformation is. This coefficient is referred to as a dilation factor. Okay, but how do we actually apply that? This step-by-step process will allow us to apply not just this transformation, but any transformation that we will go through in this video. Let's give it a shot. Let's try this example. Suppose we want to apply a dilation factor of 2 from the x-axis. First, we need to identify what the transformation is. Well, we know it's a dilation from the x-axis. That means it's going away from the x-axis, so our dilation factor of 2 must apply to the y value, not the x value. We can write this as an expression. Remember that the right-hand side is given by x prime y prime? Well, all we need to do is write that as an equation. So we have x prime equals x, and y prime equals 2y. The next step is to rearrange in terms of x and y. This is because our equations are in terms of x and y, and not in terms of x prime and y prime. Once we rearrange, we move on to step 3. This is where we substitute our new values of x and y into our original function. Now, your function is always going to be some form of y equals f of x. So when you substitute back into y equals f of x, you're going to replace y with our new value, y over 2. And x is just going to become x again. All you have to do from here is rearrange to get y on its own. And just like that, you've applied your first transformation. It doesn't matter what the function is. It could be a square root graph, a logarithm, an exponential. It's all the same. If you have a dilation factor applied to the y, then the resulting function is going to be y equals a f of x. Let's look at one more example. Suppose we want to apply a dilation factor of 2 along the x-axis. Step 1, identify the transformation. This is a dilation along the x-axis, so it needs to apply to the x values. Step 2, rearrange in terms of x and y. Step 3, substitute those new values of x and y into the equation y equals f of x. This result shows us that if you have any dilation factor applied to the x, then the result is y equals f of x divided by a. Notice something interesting here. In both examples, the dilation factors were identical. But in the first example, it was expressed as a multiplication, whereas in the second example, it was expressed as a division. This caught me off guard so many times in high school, and it cost me more than a few marks. Now sure, you can memorize this difference if you want to. That's what I tried to do. Or you can memorize this one process that applies to all the transformations. I know which one I'd rather. So let's have a look at how this process can be applied to all the other transformations. You can think of reflections as if you are holding up a mirror to the function and then drawing what you would see on the other side. Let's use the graph of root x as an example. If you are reflecting in the x-axis or about the x-axis, then the x-axis acts like a mirror. Notice that the x values remain the same, but the y values change. This means that a reflection applied in or about the x-axis actually applies to the y values. Similarly, if you are reflecting in or about the y-axis, then the y-axis acts like the mirror, so the x values are what's changing. If you're reflecting both axes, then the reflection applies to both the x and the y value. Reflections are expressed as a minus sign applied to either the x or the y value, and we apply that minus sign using the process from earlier. Suppose we want to apply a reflection in the x-axis. Step 1. A reflection in the x-axis means that the x values stay the same, but the y values change. Next, we rearrange for x and y. And finally, we substitute our new value of x and y back into y equals f of x. So, if we want to apply a reflection in the x-axis, or about the x-axis, then all we have to do is apply a minus sign to the whole of f of x. Now let's suppose we want to apply a reflection in the y-axis. Step 1. A reflection in the y-axis means that the y values stay the same, but the x reflects. Next, we rearrange for x and y, and finally we substitute back into y equals f of x. So, if we want to apply a reflection in or about the y-axis, then we need to apply a minus sign to every x in f of x. For instance, if your function has multiple x's, then it needs to apply to all of them to apply the reflection properly. Otherwise, it will end up looking different than you expect. Translations simply move a graph in any direction. It could be up, down, left or right. Okay, so vertical translations are applied by adding or subtracting from the y value. If you add, the graph goes up, and if you subtract, the graph goes down. In contrast, horizontal translations are applied by adding or subtracting from the x value. If you want to go to the right, then you add, and if you want to go to the left, then you subtract. Now, if you've been introduced to this topic before, I'm sure alarm bells just went off when I described the horizontal translation. I'll show you why that is using the process from before. First, we identify the transformation. In this example, we need to shift by a units up in the positive y direction, hence we're going to add a to the y value. Next, we're going to rearrange for x and y, and then finally substitute that back into y equals f of x, and once again, rearranging to get y on its own. We can do the exact same thing for the next example, except this time we need to subtract from y, because we're going in the negative direction of the y-axis. Now we can cover horizontal translations. First, we identify the transformation. In this case, we need to shift a units in the positive x direction, so we're going to add a to our x value. Next, we need to rearrange for x and y, and then finally, we'll substitute that back into our equation y equals f of x. Well, isn't that interesting? A shift to the right is actually described by a subtraction, not an addition. We're going to see a similar result if we try to shift to the left. A shift to the left is expressed by subtracting from the x-axis. But once we do our rearrangement, we'll see that it's actually described by an addition, not a subtraction. This is why it's important to understand where all these shortcuts come from. If you understand the underlying process as to how we got here, you don't have to memorize all of these individual intricacies. You can just memorize the process, and you'll always have something to fall back on if you ever forget the shortcut. And the best part is, this process applies to any of the transformations. So you only have to remember one thing that applies to all of your transformation questions.